I am JV Dr. Kumar Srivastava from the Department of Science under the Faculty of Education and Methodology, Jayoti Vidhyapeeth Women's University, Jaipur. Today I will discuss some theorems related on the integral domains. Now the theorem is the characteristic of a ring with unity is 0 or n is greater than 0 according as the unity element E regarded as a member of additive group of capital R of order 0 or n. Or this statement can also be written as if R is any ring with identity so that R has the positive characteristic n if and only if n is the least positive integer for which n dot 1 is equal to 0, 0 being the additive identity of R. 2. Let R be a ring with unity element E. Order of E is equal to 0, that implies characteristic of R is 0. Suppose order of E is equal to n is equal to a finite number so that n is the least positive integer such that n e is equal to 0. Let A be any element of capital R, then n a is equal to n of EA for EA is equal to A is equal to AE is equal to NE, A is equal to 0, A is equal to 0. Thus, n is the least positive integer such that NA is equal to 0. By definition, this proves that the characteristic of R is n. Now, next theorem. Every finite integral domains D is the finite characteristics. Let D comma plus comma dot be a positive integral domain so that D comma plus is a finite abelian group. We also know that characteristics of D each order of unity elements E of D comma plus. D comma plus is finite group that implies order of E is finite, that implies characteristic of D is finite. Now the next theorem. The characteristic of an integral domain is either 0 or a prime number according as the unit element E as regarded as number of the additive group of integral domain is of order 0 or the prime number. Let D be an integral domain, then D is an integral domain with unit element E. Suppose order of E is equal to n is equal to a finite number such that n is the least positive integer such that n is equal to 0. Let A be any element of D, then NA is equal to n in bracket EA for all A is equal to EA. This is NE of A is equal to 0, A is equal to 0. Thus, n is the least positive integer such that NA is equal to 0. By the definition, this proves that the characteristic of D is n. In the second level proof, if the characteristic is 0, the proof is complete. Let the characteristic be P, which is greater than 0. We have to show that P is the prime number. Suppose P is not prime, thus P is the composite integer. As we can write P is equal to P1 into P2, where 1 is less than P1 and P2 is less than P. Characteristics of P is P, that implies order of P is the P. That is order of E is equal to P, that implies PE is equal to 0. That implies P1 P2 E is equal to 0. That implies P1 in bracket P2 E is equal to 0. That is P1 E P2 E is equal to 0. That implies P1 E is equal to 0 or P2 is equal to 0 since T has the no proper zero divisor. That implies characteristics of P is either P1 or P2 is less than P. That implies characteristic of P is less than P, A, which is contradictory. Hence, P is not composite, therefore P is prime, and hence true.